Welcome to your algebra recording for the week of March 21st. We are in the last week before spring break, so that's pretty exciting. And just a quick reminder that Schoology will be available for you and Edgenuity over spring break. I will not, but you are welcome. If you're behind or you want to work on some assignments over break, you are welcome to do so. We are working in week 11, and I do have a warm-up question that's going to be very, very helpful for you as you work through this week's assignment. So I really do want you to make sure you've got your math notebook out. Remember, it is required that you are taking notes, and I want you to do this warm-up problem in your math notebook. Again, your notes are going to be very, very helpful this week. So if you've got questions, I'm going to ask to see your notes this week. So make sure you're taking notes while you're going through this recording and the lessons this week. Let's start with the warm-up question. I've got an equation, y minus 6 equals 3x, and I want you to rewrite that equation in slope-intercept form. So we're doing some review here on what is slope-intercept form. Remember, you guys have a ton of information available at your fingertips with the internet. So if you need to do a quick web search to help remind you what slope-intercept form is, you can do that. And then once you get your equation into slope-intercept form, I want you to tell me what is the slope of the line and what is the y-intercept of that line. And then graph the line. So go ahead and click pause now so that you can do this on your own. Remember, trying something on your own is going to be much more beneficial, and you will learn more when you're trying things on your own. So actively engaging in this recording. And then when you're ready to check your work with mine, go ahead and click pause. But again, if you need a reminder of what slope-intercept form is, do a quick web search. I'm going to let you work on that now. So go ahead and click pause, and when you're ready to check your work with mine, click play again. All right, so to write the equation in in slope-intercept form, let's first review what slope-intercept form is. So slope-intercept form is when we get the equation into y equals mx plus b form, where remember, you're going to have a number substituted in for this m and b variable, where m, the number that is substituted in for n, is going to represent your slope, and the number that you have substituted in for this b variable right here, that's going to represent your y-intercept. Where are you crossing the y-axis? Remember that vertical axis right here when you graph your line. The slope, remember, tells us rise over run. It tells us rise over run. That's what slope tells us. So to get this equation into slope-intercept form, right now, what we need to do is we need to get y all alone on one side of the equation and all the other terms on the other side. So I'm looking and I see I need to move this negative 6 to the other side, and then I'll have y all alone and all my other terms on the other side of the equation. So since I'm subtracting 6, I need to do the opposite to move it to the other side. So I'm going to add 6 to the other side. And I get y equals 3x plus 6. So in slope-intercept form, my equation is y equals 3x plus 6. I'm going to write that here. Y equals 3x plus 6. So what is the slope of the line? So there's my equation. What is the slope? Well, remember, our slope is the number that's being multiplied by the x term. That's what our slope is. So in this case, our slope is equal to 3. And remember, we always want to write slope as a fraction so that I have my rise over run. So I'm going to go ahead and put that 3 over 1. That's the same thing. 3 divided by 1 is the same thing as 3. Then let's go ahead and do the y-intercept. Let's identify the y-intercept. And what is the y-intercept? It is the number that is the constant term. It's all by itself. It's that b term. So that means it's going to be 6. The y-intercept will be equal to 6. So now that I have the slope and the y-intercept, I can use that information to help me graph that line. So my y-intercept is at 6. So that's telling me right here, we're going to cross the y-intercept at 6. And now I'm going to apply the slope. Slope is rise over run. So up 3, 1, 2, 3, and to the right 1. That's my slope, 3 over 1. I can also go in the opposite direction. I can go down 1, 2, 3, and to the left 1. I can do that again, down 1, 2, 3, and to the left 1. I just chose to go down because I was running out of room if I went up. And then I'm going to connect my points as best as I can, and there's my line. I'm going to go on to the next slide, so if you need more time finishing taking your notes, click pause. So this week we're going to be looking at special patterns in linear equations. That's why we took some time to review linear equations and y-intercepts and slope. We're going to look at direct variation, that special pattern. And then we're also going to look at solving systems of linear equations by graphing. So let's jump right in. So I said we were going to solve systems of equations. So what is a system of equations? A system of equations is a set of 2 or more equations. And the trick is that the solutions must satisfy each equation in the system. We'll look at an example. If all the equations in the system are linear, the system is a system of linear equations. So really the important thing is that when we have an ordered solution, or a solution, it's always going to be an ordered solution, an x and a y value. When we plug those x and y values into each equation, it's going to make each equation true. So look down here. Here's an equation of a system of equations. The first equation is 2x plus y equals 5. The second is x plus y equals 2. The solution for the system of equations is -1, 3. So again, remember, our solutions will be written as a coordinate. And remember, coordinate, we always write the x coordinate first, followed by the y coordinate. So this is telling us that when we plug in -1 for x, we should get a value of 3 for y. And that's true for both equations, because remember, the solution must satisfy each equation in the system. So let's try it. So let's look at this first equation. 2 times x, so I know x is -1. 2 times x plus y is 3, should equal 5. Does that work? So I know 2 times -1 is -2, and one second here. Alrighty, there was an error, so I'm going to start over again. So instead of saying 2x plus y, the first equation needs to be 2y plus x. So if you look, I changed this 2x to 2y plus x. So if you made some notes, make sure you correct that. And let's plug it in now, and it's going to work better. So 2 times y instead of x, 2 times y plus x. And instead of putting x, I'm going to put that plus -1, and it should equal 5. So I know 2 times 3 is 6. 6 minus 1 equals 5, so that did work. The solution of -1, 3 worked. Now let's look at the second equation. I'm going to plug in -1 for x plus y is 3. So -1 plus 3 is 2. That worked. So the solution for each equation has to work. So if we're going to have one solution that we plug in for each equation, and it will work. And that's what we mean by solving for a system of equations. So you're going to look at that this week. And when we solve a system of equations, we can have exactly one solution like we did in that previous example. We can have no solutions, or sometimes we might have an infinite number of solutions where every number we can have an infinite number of solutions. So there's 3 ways that we can find solutions for systems of for solving systems of linear equations. So there's 3 different ways that we can solve systems of linear equations and come up with the solutions. The first way is by graphing, and this is what we're going to focus on this week. And another way is by substitution, and another way is by elimination or adding our systems of equations together. But again, this week we're just going to focus on graphing. We'll get to the other methods next week, but this week we're just focusing on graphing, using graphings to allow us to solve and find our solutions for our systems of linear equations. So when we solve systems by graphing, we're going to graph our lines on a coordinate plane, just like we did with our warm-up question. And when we graph the lines, and remember, to graph the lines, we always want to get it into slope-intercept form so that we can easily graph our lines. So once we graph the lines, we look to see if there's any intersection. So let's say I graphed this line and then I graphed this line. Where our lines intersect, that is our solution. That is our solution. So we graph our lines and we look for areas of intersections, and where those lines intersect, that coordinate will be our solution. I'm going to go on to the next slide. So when we graph 2 lines, we can have one of 3 situations occur. One situation is when we graph our 2 lines, we'll just have one place of intersection. That would be our solution, just like I said on the previous slide. Sometimes we might graph our 2 systems of equations, our lines, and we might find that the lines are parallel. So they would never intersect. And if we have parallel lines that never intersect, that would mean we would only have, or we would have no solution. Sometimes we find that when we graph our 2 lines, it's a line, they have the same equation, thus the 2 lines are right on top of each other, they overlap. So when you have 2 lines that are essentially the same line and we graph them and they overlap, we would have an infinite number of solutions, because really any point on that line can be a solution because the lines are overlapping. So again, this only happens when we have the same line, when we have 2 equations that are the same, and thus we have the same line. So those are our 3 outcomes that we can have: either one solution, no solution, or an infinite number of solutions when we have the same graph overlapping. I'm going to go on to the next slide. So again, we can see now with some equations here, 2 lines, one solution. When you have the same slope, you're going to have parallel lines. So remember, same slope. If you have 2 lines and you have the same slope, you are going to have parallel lines. And when you have parallel lines, they're never going to intersect, so you would have no solutions. Here we can see that we have 2 lines that when we graph them, they're overlapping. So it's essentially the same slope. You have the same y-intercept, and thus you've got the same line. They're just overlapping, and in that case you would have infinite number of solutions. So that's kind of the same thing we just talked about. For no solutions, you're going to have same slope, but you're going to have different y-intercepts, by the way. Add that, different y-intercept, but the same slope will cause parallel lines. I'm going to go on to the next slide. So let's do this. Let's solve a system of equations by graphing. So what I'm going to do is I'm going to graph this first line first in blue. So the first thing I want to do with that first line is I want to find the slope. The slope is 2/3, rise over run. The y-intercept occurs at -2. So there's my y-intercept, here's my slope. So I always start with plotting my y-intercept, that's my starting point, and then I apply the slope. So up to the right, 1, 2, 3. I do it again, up 2 and to the right 1, 2, 3. You want to have at least 3 points before you draw in your line. So then I'm going to draw in my line as best as I can. And then we're going to do the same thing with our second line, our second equation. So we'll call this line number 2. In this one, our slope is, there's just a negative, which means -1. So our slope is going to be equal to -1. And remember, we always want to write it as a fraction, just so I'm going to put it over 1. That's the same thing. The y-intercept is equal to 3. So I start by plotting my y-intercept at 3, and then I apply my slope. Down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. And then I'm going to connect my lines, and I'm going to look to see where they intersect. And they definitely intersect. These two lines are intersecting right here at this point. And we want to find the coordinates of that point because that is our solution. So what is the coordinates of that point? We went to the right 3, and then we're not going up or down. So the coordinates would be 3, 0. So the solution, solution is going to be 3, 0. So when we plug in x equals 3 and y equals 0, it'll work for both these equations. It will make both these equations true. So that's how we solve by graphing. That's how we solve by graphing. I'm going to go on to the next slide, so if you need more time, go ahead and click pause now. You will, in Edgenuity, see examples where you will have parallel lines. And in this case, I'm not going to do this one because I'm running out of time here, but looking at both these equations, these, don't worry about those dots, they're just kind of in there. Shouldn't really be there. System of equations, I can see that both my slopes are -1. I have the same slope, so I would have 2 parallel lines here. So because I have 2 parallel lines, I would have no solutions. So remember, anytime that you have parallel lines, and remember, you can tell if you have parallel lines because you're going to have the same slope. And we also have different y-intercepts. So that's important. We know that this isn't the same line because we have different y-intercepts. So I can see my slope of both these lines is equal to -1. I see the y-intercept for both the lines are different. One of them is going to be, actually my slope would be +1 because I would have to add the x to both sides to get it into slope-intercept form. So when I add that the x's to the right sides of equations, that's what they would be. So my y-intercepts are going to be different. And because my y-intercepts are different, I know I'm just dealing with parallel lines. Because I have parallel lines, they're never going to intersect. Thus, I would have no solution. So you're going to see examples of that in Edgenuity. They're going to actually go through and walk you through, and you'll see those graphed. So again, to determine how many slopes you have, you can do that without graphing, just to determine the number of slopes. To determine the number of solutions, not slopes. To determine the number of solutions, you can do that without graphing. And you can do that by focusing on the slopes and the y-intercepts. So if you have one solution, you're going to have lines that have different slopes. They're going to intersect somewhere. If you have 2 lines that have the same slope but different y-intercepts, that means you've got parallel lines and they're never going to intersect. No solution. If you have 2 lines with the same slope and the same y-intercept, you're going to find that this line is the same line. It's right on top of each other. It overlaps, and thus you're going to have infinite number of solutions. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. Alrighty, the last thing you're going to learn about is direct variation this week. So direct variation is just a type of linear relationship that can be written in the form of y equals kx. So write that down, where k equals a constant. It's going to be, we're going to put an actual number in there. So some examples of some direct variation equations that are showing direct variation would be like y equals 3x. So again, k represents my constant. So the number being multiplied by the x represents your constant. How about y equals -2 times x? That's an example of a linear relationship that shows direct variation. So some examples of equations that do not show direct variation. Remember, we're talking about direct variation. Direct variation, we have to be written in this format, y equals kx. So some non-examples would be like y equals 2x minus 2. That minus 2 throws it off. Y equals 4x plus 5. Those are non-examples because they've got those constants added to the equations, which mess it up. So our examples are non-examples of direct variation. So direct variation, when we graph it, is going to be a line. It's going to be a line. So if you have a line, and something that also needs to be true for direct variation is that the line has to pass through the origin. Remember, the origin is that 0, 0 coordinate. So if we look here, this first graph does in fact show direct variation because, first of all, it's a line. Direct variation has a constant rate of change. That's something that's true of direct variation, and it passes through the origin 0, 0, which makes it show direct variation. Same with this second example. You can also have direct variation that's decreasing over time. As long as it passes through the origin or that 0, 0 coordinate, it shows direct variation. So you look at this last graph, and even though we're showing a constant rate of change, it's not passing through that 0, 0 coordinate. So this one would not be an example of direct variation. It's got to pass through that 0, 0 coordinate, the origin, to show direct variation. And that's how you can tell if a graph shows direct variation. You're going to have to do that this week in Edgenuity. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. All right, let me put up your key phrase assignment. Alrighty, so the key phrase that you need to answer, the question is, when looking at a graph, how can you tell if it shows direct variation? So what needs to be true of a line on a graph to show direct variation? And that's it. Directions below if you need a reminder of how to complete the key phrase assignment. If you have any questions, let me know. Otherwise, have a wonderful rest of your week.